Hi there, mathematicians. Let's get started with our first section of Chapter 10, all about lines and segments that intersect circles. Our objectives: students will be able to identify special segments and lines. Students will be able to draw and identify common tangents. Students will be able to use properties of tangents. Then our essential question is, what are the definitions of the lines and segments that intersect a circle? All right, so let's get familiar with some terminology, some core concepts in this unit. Here at the very beginning, we have a circle. Circle is a set of all points in a plane that are equidistant from the center. When we name circles, we have this small circle with a dot in the middle, and then whatever capital letter is at the center. If you look at this picture, we have a capital P right there at the center, so we name the entire circle, circle P. And then radius has an asterisk because I left this out of your notes, so go ahead and add it to your notes. It's the segment whose endpoints are the center and any point on a circle. And then a chord is a segment whose endpoints are on the circle, so super important, a chord has its endpoints on the circle. And a diameter is a chord. In other words, it's a segment that contains the center. So this chord going through the center has its endpoints on the opposite sides of the circle. All right, and then the next two vocabulary words are to describe lines that intersect our circles. We have secants. Secants are lines that intersect a circle at 2 points. So here's an example. So you must have 2 intersections through the circle, and that's a secant. A tangent is a line that intersects only in one place, and that one exact point where the line intersects the circle is called the point of tangency. So this line AB intersects the circle at point B. Now, the word tangent, not to be confused with our trig tangent, two different things. All right, so let's see if we understand these new terms. Identify all the special segments using the vocabulary that you just learned. So reference the vocabulary. All right, our first one is a segment. So you're naming segment AC. Segment AC is a radius. Segment AB is a diameter. Segment AG is a chord. Ray DE is tangent to circle C. And line AE is secant to circle C. So what's really important with identifying these segments and lines is that you pay attention to the symbols that are being used. Super important. You have a set of segments that have special names, and you have a set of lines or rays that have special names. All right, our next core concept are the coplanar circles. Remember, a coplanar means to exist in the same plane. So here we have various situations where circles are intersecting with either 2 points of intersection, 1 point of intersection, or no points of intersection. So let's talk about these 3 types. In a plane, 2 circles can intersect in 2 points. When they intersect in 2 points, then they have 2 points of intersection. They can also intersect in 1 point. All right, so these are not the only examples that we have where 2 circles will intersect at 2 points, but this is just one example to give you an idea of what it looks like. When you have 1 point of intersection, these are tangent circles. Remember, a tangent is where a common point of intersection. So when circles intersect at a common point, those are called tangent circles. And these are 2 different examples where you could have a tangent circle. where the circle's on the inside intersecting exactly at one point, and then here we have circles that are going away from each other but intersecting at one point. And then when you have circles that don't intersect at all, here's one example, and then here's a different example. When circles have the same center, they share a center, that's called concentric circles. All right, then you have 3 additional definitions. Take a moment to write all these down. All right, so let's draw and identify common tangents. So tell how many tangents the circles have and draw them. Use blue to indicate common external tangents and red to indicate common internal tangents. And these are based on the definitions that you just wrote down. So if you have to go back and reference your definitions to kind of help you, definitely do that. So let's first identify and connect the centers for each of these examples. Example A, B, and C. So when you draw the segment that joins the centers of the 2 circles, it should look like this. Next, let's draw the common tangents. Remember, use blue to indicate the common external tangents and red to indicate the common internal tangents. All right, so part A, example A, has 4 common tangents. 2 that are external, that's the blue, and 2 that are internal, that's the red. Example B has 3 common tangents. 2 that are external, remember those are the blue, and 1 that is internal. And then example C only has 2 external, no internal common tangents. All right, here's our first 2 theorems of Unit 10, and Unit 10 has a lot of theorems, so definitely take time to learn them section by section. You will not have access to a formula chart for this unit, although I'll give you a reference chart that you can use for at all times as you practice, so definitely get very familiar with each set of theorems day by day. All right, let's take a look at our first one, our tangent line to circle theorem. It states that in a plane, a line is tangent to a circle if and only if, that's our biconditional, if and only if the line is perpendicular to a radius of the circle at the radius's endpoint on the circle. And we have an implied statement for this theorem. So get familiar with that. It shortens it down to tangent to a circle implies line is perpendicular to radius. So here's our example. If we have a tangent line to a circle, then the radius is going to be perpendicular. Like that's true every time. All right, an external tangent congruence theorem. Tangent segments from a common external point are congruent. In other words, implied tangents from external point implies congruent segments. This one's pretty easy. Basically, here's our external point S, and RS and TS are tangent, meaning they intersect at exactly one point R, and exactly one point T. Both these tangents come from the same external point. So that means that these segments are congruent. They're equal in length. All right, so here's an example where we have our theorem in action, where we're going to verify a tangent to a circle. Now remember, in order for it to be a tangent to a circle, so for this situation we would be looking at deciding if ST, segment ST, is tangent to circle P. And based on our theorem, the tangent line to circle theorem states that if line M, or in this case ST, is tangent to the circle, then the line is perpendicular. So all we need to prove here is that we've got perpendicular right here at the tangent and the radius. So if the tangent and the radius form a right angle, in other words, if this is a right triangle, then we have proven that ST is tangent to circle P. So let's make an observation. We can conclude that segment PT is the radius to circle P. We can also use the converse of the Pythagorean theorem to decide whether the triangle is right, acute, or obtuse. So we set up c squared, and then we're not sure what the relationship is between c squared on the left side and a squared plus b squared on the right side. So the longest side is 37, so that must be our hypotenuse. All right, so square each of these values, resulting in 1,369 compared to 1,225 plus 144. So go ahead and add on the right side, and you get a result of 1,369 on the right side. So here we see that it is a true statement. They're both equal to each other, so we can conclude that this is a right triangle. And since it is a right triangle, we can conclude that this is segment ST is tangent to circle P, because we have a right angle at ST and PT. All right, we're going to find the radius of a circle. So in the diagram, point B is a point of tangency, so find the radius of circle P. So again, when a tangent and a radius meet at the point of tangency, in this case, so we have our tangent and our radius meeting at the point of tangency, point B, we want to know if this is a right angle. Actually, we know that this is a tangent and we know this is a radius, so it does form a right angle. So we don't even have to try to figure that out. It is a right angle. What we're trying to figure out is what's the radius. So we're going to use Pythagorean theorem because this is a right triangle. Note your hypotenuse is all of this segment here. So it's the 50 length plus the r length. So you have to put it in as an expression. And then you have 80 as one of your legs and r as the other leg squared. Note 50 plus r squared. Make sure you expand so that you see both expressions, because this means you're going to have to FOIL or double distribute. So you end up with 50 times 50, and then 50 times r plus 50 times r again, plus r squared. So this results in 2,500 plus 100r plus r squared equals, and then 80 squared is 6,400 plus r squared. Subtract the r squareds from each side. So our r squareds will zero each other out, leaving you with 2,500 plus 100r equals 6,400. So you're going to subtract this 2,500 to combine it with the 6,400, resulting in 100r equals 3,900. Then divide both sides by 100. So our radius is 39 feet. All right, here's our first construction of Unit 10. So take a moment to pause the video and follow each of these steps using your given circle C and point A that are on your note pages. And just follow this step by step. So complete step 1, here are the directions, and this is what it should look like when you're done. Step 2, here are your directions, and here's what it should look like when you're done. And then step 3, and this is what it should look like. So just try this on your own and see how it goes. All right, and then our last example, we're going to use our properties of tangents to find the value of x. So here we have segment RS is tangent to circle C. So that means it's tangent at the point of S. And then segment RT is also tangent to circle C at T. So that means both these tangents are coming from the same external point. Well, just a reminder, one of your theorems states that tangents from the same external point implies congruent segments. So that means we can conclude that this segment is equal to this segment. So we start off by saying segment RT is congruent to segment RS. Substitute 3x plus 4 in place of RT and 28 in place of RS. And then solve for x. So we subtract the 4 on both sides, resulting in 3x equals 24. Then divide both sides by 3, resulting in x equals 8. All right, here's a cute image of a squirrel trying to rotate inside of a circle, otherwise known as a hula hoop. All right, bring your questions, clarifying questions tomorrow. Be ready to practice this first section of circles. See you soon.